I'm Manu Rathore. I'm a part of the TENNLab research group working on neuromorphic architectures. Primarily, we'll be talking about the network on chip for the spiking recurrent neural networks that we are working on. So let's get started. I'll just briefly talk about what the motivation is around this. It relates to the talk Katie had yesterday a little bit. Then I'll discuss like the proposed architecture and how we are leveraging the sparsity in the neural network to save resources on chip. And we'll also discuss like results, which will mostly be like area on chip, throughput, and stuff like that. So the recurrent neural networks, I guess like everyone knows what they look like. So we are primarily interested in like smaller smaller spiking recurrent neural network with sparse connectivity because they can achieve like high computational power despite having less number of neurons. And so our kind of motivation comes from there. So what the network on chip kind of requires, I'll just briefly talk about what we need from the network on chip that we have. So basically, we want to have a network on chip that enables connectivity between any two set of neurons on the chip. Then we also want it to be like low power, area efficient, all those good things. We also want to preserve the spike timing information because that's really where a lot of the information is encoded in the form of. We want it to be scalable. And we also want flexibility in design space to have like multiple viable routing paths through the network between a set of neurons. We look at them from the perspective of circuit switched versus packet switched, like on chip. Everyone knows that they're basically constrained by physical wiring. So existing solutions are mostly packet-based. A lot of work has been done on packet-based architectures, which are mostly address event representation-based architectures. But we find that for proximal neurons, for example, if two neurons are like right next to each other on chip, you don't want to like encode the spike. You want to just send it. So you do need a reconfigurable architecture, which is not packet-based, but more of circuit-based architecture. But there, like a lot of people use crossbars for that. But the problem with crossbars is you don't have multiple viable routing paths. So if you have, for example, if one of the switches is, say, not working, or yeah, I mean, you cannot leverage the sparsity as well, which I will come to in the later part. So that's why we primarily want multiple viable routing paths, which would give us the capability of leveraging the sparseness in these networks. We also don't like crossbars because it scales multiplicatively. So the motivation is kind of networks that look like this. So this network was trained using EONs. It has 72 neurons and 89 synapses. And as you can see, it's like not a lot of neurons, it's just 72 neurons. And the connections are just 89. So you don't need a lot of physical wires going through it. But you still do need the reconfigurability of it. So this is the motivation from where the proposed architecture comes from. So we use a class-based topology, which is like a telecommunication kind of network. In the class network kind of uses smaller crossbars to establish connections between the input and the output, but it divides it into this multi-stage approach, which ends up not only giving you lesser number of switches that you need to implement it, but also multiple viable routing paths. So because of these multiple routing paths, so for example, if you look at all the inputs, you can actually reach any specific output through multiple paths through this multi-stage network. And it's delay agnostic. So it's kind of by architecture, it preserves spiking information. You can like kind of use constraints to have it to be delay agnostic. So it primarily converts the problem of connecting like this whole capital P total inputs to capital P total outputs into like a smaller problem. And that's how we get all this area savings from this approach. This is just a condition which we have to like satisfy for the number of crossbars in the middle stage, so that you have like any input can connect to any output all at the same time. So it's basically a non-blocking approach. So you can think about when you look at a spiking recurrent neural network, you think about how many neurons are there. So if you have, for example, say n neurons, you think about like n neurons want to connect to like the n-1 other neurons. But the problem is on hardware, the connectivity is also limited by fan in and fan out of the neurons. So that's how we come up with the Cmax, like the number of maximum connections for a specific sized neural network with a given like fan in and fan out of the neuron. We relate that number to the number of connections we can get from this network, and that's how we design the class network for a specific spiking recurrent neural network. So how we leverage the sparsity is we play with the number of crossbars in the middle stage. So it kind of gives us, you can still connect any input to any output, but you will actually, it won't be non-blocking in the sense that you cannot connect all the inputs to all the outputs at the same time. And that's what is leveraging the sparsity in the in hardware, basically. So we define it as concurrent connectivity, and that's what we play with. We say that concurrent connectivity of a specific network on chip, we can kind of change it or basically reduce it while ensuring that any input, any neuron can connect to any other neuron on the chip. So we come up with a measure of concurrent connectivity percentage based on assuming that all the connections are unicast. I actually didn't talk about it, but you can also do like broadcast and multicast through this. But the expression becomes really complicated. So we assume the unicast connections and come up with a concurrent connectivity percentage for a specific network. And so I guess I'll just reiterate what the main idea is here. So first, we are using a circuit switch class-based network, which kind of does away with all the packet-based, like the spike encoders, decoders, routers, and all those things. And the second thing we are doing is we are leveraging the sparseness by changing the number of crossbars in the middle stage, which gives us the opportunity of having a network which is kind of, gives us multiple viable routing paths, but not all of them are active at the same time. And that's what we want. So yeah, and the good thing about this network is also because it's like dedicated wired paths are provided through the switches, you can build an analog or digital kind of spikes. You can use it for analog or digital spikes. We have done here like a digital implementation which uses multiplexer-based crossbars. We have synthesized it to 65 nanometer CMOS NLP process, and all the results are from post-layout simulations. But this graph shows how the number of in terms of number of switches, how the SpikesNet or the proposed architecture compares with the crossbar. This just shows that as you vary the concurrent connectivity, you can kind of see like with this bar graph, the trend kind of the slope changes as you increase the number of neurons in the neural network. So as you increase the concurrent connectivity, the amount of area that your network needs doesn't scale as badly if you use the concurrent connectivity aspect. The other graph actually shows the area on chip, which is from the from Cadence Innovus. We did the post layout of that and varied the concurrent connectivity to see how the area looks like. This is just showing a comparison of you can see my cursor, right? Yeah, this is just showing if you use a concurrent connectivity of 37.5%, how the relative area changes as you increase the concurrent connectivity percent, but then also when you compare it with a strictly non-blocking or some other architecture or some other networks in the literature. This is how the latency, throughput, and energy per spike numbers look like. They're like pretty small, I would say, for a circuit switch network, because it's all just 3 switches. It's a combinational network, basically. So that's how long the spike takes to travel from the input to the output of the network. This is just showing a comparison with other approaches in the literature. The main thing is the packet size, which is like just 1 bit, which is different from, as you can see, like the packet-based approaches would have multi-bit addresses. And so all these multiple wires are basically being like metal traces running on the silicon, basically. So you don't need to do that like for a smaller network. And the throughput is kind of comparable with the other approaches, given that it's circuit switched. We see like basically 4.5x savings in area as compared to other packet-based NOCs for non-blocking network. When we use a concurrent connectivity and reduce the number of crossbars in the middle stage, so that only 75% of the total connections are supported, we get a 6.3x savings in area. We get a 9.9% higher throughput, and then substantial savings in power as well, because there is no dynamic power related to clocks. So to conclude, I guess this is like a really good approach that you could use for proximal neurons. And you could also leverage the sparsity, because most of the networks that we have don't need all the connections to be established at the same time. And so that's what we are leveraging in this case. I guess that's it. Thank you.